Operations on radicals. Multiplication. Good luck.
Okay, multiplying radicals is actually just the same thing as multiplying anything else. And you'll see in this first example what I mean. Okay, the first method here is just going to simplify after multiplication. So we're going to multiply the 2 times 4, which gives me 8. And now we're going to multiply root 7 times root 75. So we need 7 times 75. That gives me a whole 525. Okay, and now technically I'm done, except for the fact that I have to simplify this to write a final answer. That gives me 8 times, oh my goodness, something that divides into 525, that's a perfect square. 25 does. And so I'll write 25 times 21, by the way. Now I get 8 times root 25, which is 5, times root 21, which is root 21, and 5 times 8, that gives me 40 square root 21. Okay, so that's one way that we can do it. Second way is to do a quick simplification first. So we'll do 2 root 7 is already simplified. We can't go any further than that. 4 times the square root of 75 is 4 times the square root of 25 times the square root of 3, which is 2 root 7 times 4 times 5 is 20 times root 3. And so now I multiply 20 times 2, which is 40, and 7 times 3, which is root 21. Okay, I mean, either way you get to the same answer. It's just a question of, do you simplify after the multiplication or before the multiplication? Now, what's the general rule that I've been using here? Well, this is one heck of a rule to read the first time through. But let's read it, and we'll realize that it's just not saying that much. All it's saying is I've got 2 different radical expressions, and I'm multiplying them together. The m and the n, the coefficients, they got multiplied together to give me m times n. And the a and the b, the radicands, they get multiplied together in the radicand to give me a times b. And what's really valuable here is to notice that the k is the same k. This is a requirement that it must be the same k in both cases in order to do this. Okay? Now, down below here is quite a lot of math language, but what's all this saying? All it says is k is a natural number. So k is the numbers 1, 2, 3, 4, 5, 6, whatever. It's saying a, b, m, and n are just any real number. They're just numbers in R. And finally, the last 2 requirements, well, those are the restrictions on a and b. A must be non-negative. If it's negative, then this thing isn't necessarily existing. And b must be non-negative as well. And I should specify that these restrictions on a being non-negative and b being non-negative are only true if k is even. If the index is odd, we're allowed to have negative values of the radicand. Wow, that's a lot of different little restrictions in that final line. Okay, but the idea of this rule is the main larger font here. Multiply the coefficients and multiply the radicands. Okay, let's take a look at a couple examples. So multiply and simplify. In the first example here, there's only one coefficient to multiply, and that is the 5. So 5 times 1 is 5. And 3 times root 6, that is root 18. Can I simplify this? You bet I can. Root 18 is root 9 root 2, since 18 is 9 times 2. Root 9 is 3, so 5 times 3 gives me 15. And root 2 just remains root 2, and I'm done. Okay, in the second case here, whoa, this is going to be a monster multiplication. Let's go ahead. I'll multiply first 2 times the cube root of 11 times 4 times the cube root of 2. That gives me 8 up front times the cube root of 22. In the second multiplication, that's 2 times the cube root of 11 times negative 3 cube root 3. That'll give me minus 2 times 3, which is 6. And then inside the radicand, I've got the cube root of 3 times the cube root of 11. That's 3 times 11 is 33. Okay, and in fact, I am now done. Okay, on the next page, we've got 2 binomials multiplying together. Actually, why don't you pause and try that, and I'll just start taking it up right now. If you'd like to pause and try it yourself first, that's great. So 4 root 2 times root 7 gives me 4 root 14. 4 root 2 times negative 5 root 14 gives me 20 times the square root of 28. 3 times root 7 gives me 3 root 7. And finally, 3 times negative 5 root 14 is negative 15 root 14. Okay, is there any simplification possible? Well, there's 2 things at least that I can do here. First, in terms of simplifying, the only one that can be simplified is the second term. So I'll rewrite all the others as is. Okay, so root 28. Well, on the side here, I'll just note that root 28, that's 4 times 7. And so that becomes 2 times root 7. Okay, that's just a little side note. So now I can rewrite this as negative 20. Oops, my bad, I'll erase that. I'm multiplying by 2 root 7, so that's now negative 40 root 7. There, okay. Now, can I combine some things? Yes, I can. In terms of root 14s, I've got this term here and this term here. Combining those together gives me negative 11 root 14. And in terms of root 7s, I got this one here and this one here. So those 2 terms, if combined together, gives me negative 37 root 7. Okay, last one, again, pause it if you'd like, or you can just watch as I do this. So 7 root 3 times this binomial. Well, let's multiply 7 root 3 times 5 root 5. That gives me 35 root 15. Second multiplication, I get negative 7 times 6 is 42. Root 3 times root 3 is root 9. Hey, notice root 3 times root 3 gives me root 9. On the side here, let's just take note of that. Root 3 times root 3 gave me root 9. And what's the square root of 9? Well, that's 3. Does that make sense? If you take the square root of a number times the same square root of that same number, the result you get back is the original number itself, 3? Well, that should make sense. That's the definition of square root. Okay, so let's simplify this now. 35 root 15 is just 35 root 15. Root 9 is 3, and so 42 times 3 is 126. All right, that's it for multiplying.